We are back and we're going to do our last topic for this chapter in our next segment. And it is a much more restricted reaction. That's why we're going to spend so little time on it compared to the electrophilic aromatic substitution, which we studied for the first day of this chapter. We're going to look at nucleophilic aromatic substitution. And let's just read this little box first before we think this is the end-all be-all reaction. This reaction is much more limited than electrophilic aromatic substitution. There must be a nitro group that is ortho or para to a leaving group. So in both examples here, I have that situation. I have a leaving group that's a chloride here, and we don't usually think of fluoride as a leaving group, but in this case, it actually is a very good choice for reasons we'll discuss shortly. Here's a strong nucleophile. You must have a strong nucleophile. So let's highlight that. Must have a strong nucleophile. Or else you don't, it's a deal breaker if you don't. And you also have to have this stipulation here. There must be a nitro group that is ortho or para to a leaving group. And we have that right here. We have a strong nucleophile called ethoxide. We've got the mechanism here. Don't worry, we'll do our own practice mechanism shortly. Why does this reaction happen, and why is it so different? Well, we're not generating an electrophile here. It's not electrophilic aromatic substitution. Our nucleophiles here and our electrophiles here. You can't do an SN2 reaction on an sp2 carbon because the bond to the halogen's too strong. sp2, 33% S, compared to our normal SN2, which is a sp3 carbon with a leaving group, that's 25% S, weaker bond. So what happens instead, the nitro group is withdrawing electrons so strongly. Think of this, the nitro is actually causing this kind of thing to happen, which makes all the carbons in the benzene feel more positive. The carbon with the chlorine already feels positive because chlorine's more electronegative. That draws in the nucleophile here, and resonance. You can think of it as like a 1, let's see, a 1, 2, 3, 4, 5, 6, 7, 8, a 1-8 addition with those arrows. I hope that means something to everybody. A 1-8 addition up there. The electrons hit position number 1 and flow all the way up to 8. And then they resonate back. The nitro group resonates back and kicks off the leaving group. What do you call it when you make a pi bond and kick off a leaving group? We have a word from the past, elimination. What do you call it when you put a new group on a position? Addition. We added the OET here in the first step, and then we eliminated the leaving group in the second step. The overall process is called addition elimination. And another way to say it is nucleophilic aromatic substitution. Nice. Same story happens here. The rate determining step is the addition. That's the one that destroys aromaticity. So much like electrophilic aromatic substitution, the first step gets rid of aromaticity, creating an sp3 carbon, which you can't resonate through. And if you can't resonate in the cycle, you're not aromatic. So addition's rate determining, which is why fluorine is even better than chlorine, because it makes the carbon feel more positive over here than the carbon did over here. Not quite as positive. So that'll speed up the rate determining first step. has nothing to do with fluorine's abilities as a leaving group, which is not that good. Fluorine does not like leaving. It's not a stable anion, but it draws the nucleophile in, and cyanide is a strong nucleophile. Got that going on here. Electrons resonate all the way up to the nitro. Would this be a 1,8 or a little lower? It hits here, call that 1, flows up all the way 2, 3, 4, 5, 6. It's a 1,6. I'd also like to point out that if you started with the other resonance form of this first one, the other benzene resonance form, you would have not had to have used the 1,8 addition to get the same result. So let's get a little mechanism practice here. We have OET minus as our nucleophile. And we've just learned some new stuff. Let's incorporate our ability to simplify things or shorten them, not really simplify them. Do red first. I don't think we can do the blue second. Can we combine these two? We really can't, because in this mechanism here, we need this pi bond, and we don't have it to start with. We can't combine. Oh well, I got excited for a second. It's fine. We got to do it in 2 steps. There's no short form. That wouldn't be a 1,8, would it? If you hit down here, this looks like our first conjugate addition we ever did. Remember, this is called conjugate addition. It's an addition that involves resonance. That's what conjugate means. And this time it's not 1,8. I believe it's our classic 1,4. It hits here. 1, 2, 3, 4. And we create a different intermediate, but our result will be the same. There's your leaving group. There's your OET. And here's your nitro that's double bonded. Nitrogen still has 4 bonds and a positive charge. Can resonate either oxide back. We can do this one just for variety. Whoa, my pen went off. Resonate back. Resonate here. And do your elimination. And get to the same place when we're all said and done. Okay, beautiful. And now let's talk about this one. I don't think there's an alternate mechanism to talk about. We could take this opportunity to review how we can make these reactant molecules, because we're supposed to be able to do that as well. If you put the questions now are, how do I make this? And how do I make this? And let's just deal with those since we're here. It's all about starting with benzene on our test. So let's start with benzene up here and make our 2 targets. We'll make this target here, the one on the top left of the screen. And we'll make this target on the top right. The fluoro. And NO2. Okay. Well, of the 2 groups on here, we're talking about traditional electrophilic aromatic substitution to get to this point so we can do our new reaction, where there's the new reaction has a leaving group ortho to a nitro. That's a candidate for nucleophilic aromatic substitution, or a leaving group para to a nitro, also a candidate for nucleophilic aromatic substitution. To get to these points, we need to use our traditional electrophilic aromatic substitution. Now, if you want to put the nitro group on first, you're going to have trouble, aren't you? The nitro group is a meta-director, means the second group will not go in this ortho position that you want it to, and you will lose points. Put the chlorine on first. It is an ortho-para director. We were reviewing those this weekend, weren't we? How do you put a chloro group on benzene? Use Cl2 and FeCl3 or just Fe. And that chlorinates. And then the next group, you're going to get nitro in the major product in this next reaction. The major product will actually have nitro para. And you're saying, oh, I can't even get a 50% yield. I'm going to fail. Nah, that's not true. Sacrificing chlorobenzene, which is dirt cheap, is not going to cost you here. How do you put a nitro group on after? You put HNO3 and H2SO4, and you'll get the para major. We'll even put that down here. Plus para major, and you get the ortho minor. You take your lumps and you separate the two, and you get your ortho nitro chlorobenzene. I guess you should call it ortho chloronitrobenzene, shouldn't you, for alphabetizing reasons. How do you get, there's going to be a little more involved here. I might move that one down. Maybe I can't. No, of course. Of course. I'm not even going to try. I take it back. Oh, look at that. That's cute. There. How am I going to get over there? Once again, if you put the nitro group on first, the next group goes meta. That's not good. Fluoro group on first, which we don't know how to do directly. We got to remember how to get a fluoro group on benzene. That involved a lot of steps, but at least once we get it on there, fluoro group is an ortho para director, and my major product will be the para nitro fluorobenzene, and we'll get ortho minor in our last step. And we'll separate them out, getting a better yield of the one we want. But yeah, how do you get a fluorine on there first? We don't know how. You can't put F2 and then Fe. It's not that it's not going to work. F2 is so reactive, you're going to get hexafluorobenzene. That's how reactive F2 is. So you can't stop at one. So you get the proverbial dog's breakfast if you tried to stop at one fluorine. We do know how to convert an NH2 group to a fluoro group. I want to remind you that's one of the 7 reactions after diazotization. Maybe I'll bring that up onto the screen for us so we can quickly review that protocol. I'm trying to find it on the other screen, and I found something. And yeah, we're at the end of chapter 22 there. Got homework problems I was looking at. What else we got? Where's that? There, that's the classic thing I'm looking for. It's the only time we learned how to put a fluoro on benzene. You had to come from a diazonium ion. Diazonium ions come from aminobenzene, also known as an aniline, and aniline comes from a nitro compound. I can't stress enough. Getting here involves putting a nitro on first and then reducing it with one of our 4 methods we learned. Then you do this process to get to the diazonium ion. Then you do this process with room temperature and fluoroboric acid to get the fluorine. Let's see if we can remember all those steps starting from benzene. We got benzene, and I want to get a nitro on there. Not yeah, nitro. Wow, it's not this nitro though. Oh, so confusing. We're putting a nitro that's going to become a fluoro. HNO3, H2SO4, and then I need to make it into an NH2. How do you make it into an NH2? I'm going to draw an intermediate in here. How do I make that into an NH2? It's a staple reaction. We have to learn it. I'm putting it down here for a reason because it's going to become a fluoro. And H2 and nickel was something we did just recently. And now you've got NH2. You've got two more things to do now. Convert NH2 to a fluoro, which is not a one-step process either, and then introduce a nitro in the para position. Once you get the fluoro on there, or you can put the nitro on first. Interesting. This is also an ortho para director. You could put the nitro on first and then convert the NH2 to a fluoro. That would be a faster way to do it because NH2 is the strongest director we have for electrophilic aromatic substitution. Or you can convert the NH2 to a fluoro first. It's still an ortho para director. It's going to slow things down. But hey, this is a lecture course. I'll give you full credit no matter which approach you use from this point on. I am going to do the first one. I'm going to put the nitro group on. HNO3, H2SO4. Then I'm going to diazotize. I'm going to diazotize my nitrogen. What does that mean? What does diazotize my nitrogen mean? It means convert it to a diazonium ion using this protocol. You have to know this protocol. That protocol being NaNO2, NaNO2, HClAq, 0 degrees Celsius. So now you're at the stage where you have an N triple bond to N here. And step 3, you got to convert that to a fluorine, and that involved HbF4 and room temperature. And that makes this so that we can do our nucleophilic aromatic substitution at the top of the screen. So we got a sneaking in review at all possible opportunities here. And we're going to do, after we come back from break, we're going to do a roadmap review to bring all of this into context, we hope. And I will see you after break.